Okay, so let's go through this transformation stuff. So we talked about the fact that transformations can be described from that equation, AF b bracket x minus h plus k, and that you have to memorize what the four parameters do. And it's not necessarily what letter is used, it's the position that it's in. A is always in front of the function, B is always in front of the x. The x minus h is in brackets. H is hooked directly onto the x with a plus or a minus, and k is outside the bracket. So we know that A causes a vertical stretch by factor of A, and when it's negative, it reflects over the x-axis. B causes a horizontal stretch, but the stretch factor is the reciprocal of B, and when B is negative, it reflects over the y-axis. H shifts the graph left and right, and remember the value of H is always the opposite of what it appears to be because the minus sign is there in the general equation. And K shifts it up and down. So, looking at this first question, given y minus k equals a bracket x minus h all squared, where it says h is negative and k is positive. H is less than 0 and k is greater than 0. So what we normally did is we got the y by itself, in this case by adding the k to both sides. And then if h is negative, that means the graph is going to go to the left. And if k is positive, the graph is going to go up. So if you take a point, and I guess the other thing you have to remember is that this is a transformation of y equals x squared, which starts at 0, 0. That's where the vertex is. But it's going to shift to the left and up, which will put the vertex in quadrant number 2. Remember that the quadrants are labeled like that, right? 1, 2, 3, 4. So the vertex will be in quadrant number 2. Number 2, given those functions f and g, the transformations that will transform f to become g would be translations of what? Okay, so these are both transformations of y equals the absolute value of x. And if we take the starting point for those graphs, there is a name for that point. It's called a cusp. But these absolute value graphs, remember, are big V's. So the cusp is where the graph starts. So f, the cusp of f, would be at the point 2, 3. Because the graph of x minus 2 plus 3 would be shifted 2 to the right and 3 up. Where for g, the cusp will be at negative 2, 1. So therefore, to go from positive 2 on the x-axis to negative 2, you got to go 4 units left. And then go from positive 3 on the y down to positive 1, you have to go 2 down. And that's why A is the correct answer. Number 3, the transformation of the function f at x equals x cubed is described by the mapping notation given there. So describe the transformations of y equals f at x. Well, if x maps into x minus 4, that means all the x values are decreased by 4, or the graph is going to go 4 units left. And if y is mapped into y plus 9, that means you're going to add 9 to all the y values, which means it's going to go 9 units up. The next one says the graph of y equals f at x is transformed into g at x plus 4 equals 2 f at x minus 3. The domain and the range of each function is shown below. So domain and range of the graph of f is given. And then for the graph of g, you've got those values a, b, c, and d. So what are the values of a, b, c, and d? Well, once again, to get g at x by itself, we would subtract the 4 from both sides. So it would look like that. And we have an a value of 2. All right, so you got to remember that that causes a vertical stretch by a factor of 2. So all the y values get multiplied by 2. And then they would be decreased by 4 because that is our k value. It might be helpful to write a mapping notation for this. So the only thing that's going to affect the x is the x minus 3. That means that h is positive 3, so the graph will go 3 to the right, or you're going to add 3 to all the x values. For the y values, you're going to multiply them by 2 and then subtract 4. So that's our mapping notation. So if we take our domain was at -1 to 3, and all those x values would be increased by 3. So it would become 2, 6. And those are our values of a and b, 2 and 6. Our range was from 2 to positive 6. All those values are going to be multiplied by 2 and then decreased by 4. So when you multiply the 2 by 2, it'll be 4. Decreased by 4 becomes 0. The positive 6 is multiplied by 2 to get 12. Decreased by 4 gives us 8. So those are the values of C and D, 0 and 8. I'm going to be here till about 5 o'clock. Okay? So, I mean, don't worry about cleaning my room tonight. It's no problem. No problem. Okay? If you want, yeah, sure, absolutely. Yeah. Yeah, don't worry about it. It's fine. Okay, on the next page, the graph of f at x is transformed to produce the graph of g. So we're going from f to g. What's an equation for g in terms of f? Notice that this says SC beside it. That means it's a standard of excellence question. So on the diploma exam, I think it's 80% acceptable standard questions, and then only 20% would be the harder ones, which are standards of excellence. So that's what that SE means. So to go from F to G, remember you always do your stretching and reflecting first. Now this graph hasn't been reflected because both graphs point upwards, but it has been stretched for sure. Okay? It has been stretched for sure. So one way we could look at that is compare the two starting points. That would be one way. Another way would be to actually compare points. Okay, so if we took the starting point of 1, 2, the new starting point is 3, 4. So our x value of 1 became positive 3. So that means the x value was multiplied by 3, or it was horizontally stretched by 3. Try that again. And remember that when you have a horizontal stretch, that's our B parameter, but also that B and the horizontal stretch factor are reciprocals of each other. So B would have to be 1/3. And then when we look at the Y value of positive 2, it becomes positive 4. That means there's been a vertical stretch. A vertical stretch by a factor of 2. And that means that A is 2. Now, the reason you know that there's a stretch here and not just shifting is because the shape of the graph has changed. Okay? G, you can see, is much wider than F. So that tells us that it's been stretched. So we know we just can't say, well, it shifted 2 units to the right and 4 up. That would give you the right starting point, but it wouldn't give you the right shape of the graph. So that's how we know that it was stretched. So we're looking for the equation that has a B value of 1/3 and an A value of 2, which is equation D. Okay? Do you have this first booklet right now? There's more over there on the counter. Yeah. The graph of F below is vertically stretched by a factor of 2 about the x-axis, horizontally stretched by a factor of 1/2 about the y-axis, and then translated 3 units up. So this asks us to sketch the graph of the new function. And again, this says it's a standard of excellence question just because of the number of transformations. So remember, you always have to do your stretching and reflecting first. So if we vertically stretch by a factor of 2, all the y values would get multiplied by 2. And at the same time, we can horizontally stretch by a factor of 1/2. That would multiply all the x values by 1/2. So let's take the key points on this graph. This graph starts at -10, 0. All right, if we horizontally stretch by a factor of 1/2, you're going to take half of the x value, and vertically stretch by a factor of 2, you're going to multiply the y value by 2. Now in this case here, 0 times 2 stays 2. And then it has to go up 3 units. So when you add 3 to the y value, it'll become positive 5. So I just want to check that one more time. I started at -10, 0. I horizontally stretched by a factor of 1/2, so the -10 became -5. Well, I did write a 2 there, I shouldn't have, because I multiplied by 2, so that stays 0. And then that'll be not positive 5, but positive 3. There we go, that's better. The next point on the graph, the next key point is the point -4, -4. So if we horizontally stretch by a factor of 1/2, we take half of the x value, which is -2, multiply the y value by 2, that'll be -8, and then it has to go 3 up, so -8 plus 3 is -5. The next point, the major point on this graph, is the point 2, 0. So we're horizontally stretching by 1/2, we're multiplying the x value by 1/2. We're vertically stretching by 2, so you multiply the y value by 2, which stays 0, but then you add 3. Whoops. Then you add 3. So it'll be 1, 3. The next key point on this graph is the point 4, 3. Horizontally stretched by 1/2 will give you 2. Vertically stretched by 2, multiply the y value by 2 gives you 6. And then it's going to go up 3, so that'll be 2, 9. Then we have the point 6, 0. Horizontally stretched by 1/2 gives us 3. Multiplying the y value by 2 stays 0. But then when we add 3, we get the point 3, 3. And the last point is 8, -1. Horizontal stretch by a half, the x value is multiplied by a half, which is 4. Multiply the y value by 2, gives us negative 2. And then when you go up 3 units, it'll be 4 comma 1. So now we can put all these points on there. Negative 5 comma 3. Negative, something's not right there. That's negative 2, negative 8. I'm not sure why I wrote negative 5 there. That's negative 2, negative 5. So negative 2, negative 5 is right there. Then I have 1 comma 3. Then I have 2 comma 9. 3 comma 3. And 4 comma 1. So here's our new graph. Something like that. So we've done this. We use this procedure quite a bit where we just pick all the points, the main points on the first graph, and then we do all the transformations to each point. Number 7 is also a standard of excellence question. It says the graph of f is reflected in the x-axis, stretched vertically about the x-axis by a factor of a third, stretched horizontally about the y-axis by a factor of 4 to create the graph of g. The point negative 3 comma 6 is on f. What is the corresponding point on g? So again, what makes this a standard of excellence question is just the number of transformations that are being done. If you reflect it about the x-axis, that means the positive 6 value of y will become a negative 6. If you vertically stretch it by a factor of a third, you're going to multiply the y value by a third. So the negative 6 will become negative 2. If you horizontally stretch by a factor of 4, you're going to multiply the x value by 4. It will become negative 12, negative 2. And that's your final point. And by the way, all these questions in this booklet have come off old diploma exams. So these are the types of questions that you're going to see. On the next page, the ordered pairs below represent possible transformations of the point P, A, comma, B on the graph of the function y equals f at x. If f at x undergoes the following single transformations, identify the coordinates of the corresponding point P on the new graph. The first one, the corresponding point on the function y equals negative f at x. So when you have a negative sign in front, that means you're going to reflect it over the x-axis. That means that all the y values get multiplied by negative 1, which is what point 3 shows. If you go from a comma b to a comma negative b, right, you're always starting at a comma b as your starting point. In this case, if you reflect over the x-axis, b will become negative b. You'll multiply the y values by negative 1. So again, that is point 3. For y equals f at 1/4 x, so that's a b value of 1/4, and we learned that that causes a horizontal stretch, but the stretch factor is the reciprocal of b. So horizontal stretch by a factor of 4 means the x values are multiplied by 4, which is what point 1 shows. A becomes 4a. B doesn't change. For y equals 1/4 f at x, that's an a value of a quarter. That is a vertical stretch by a quarter. You're going to multiply the y values by a quarter, which is what 0.4 shows us. Multiplying by a quarter is the same as dividing by 4. And that's done to the b value. The last statement, it's y equals f at negative x. So a negative in front of the x, that's a b value. That causes a reflection over the y-axis. So a would become negative a. And that's what 0.2 shows us. So remember that on the diploma exam, just like on our unit exams, there are 4 boxes. You're going to put your numbers in there. But what the computer marks, it marks what you bubble in below. Okay? So this one is very straightforward because there's 4 digits. But you always work left to right. So if you get an answer of 1 digit, you just use that first box on the left. 2 digits, use the first 2. When the graph of y equals negative x squared plus 4 is reflected in the y-axis, what is the new equation? Okay, to get a reflection in the y-axis, you're going to replace x with negative x. And because the x is squared, the negative x will be squared as well. And when you square negative x, it becomes positive x squared, but the negative sign in front keeps the negative there. So it turns out that it's the exact same equation. If you take the graph of y equals negative x squared plus 4, and we can look at it, once you see it, it's the graph of x squared reflected over the x-axis, so it goes downwards and shifted up 4 units. Well, what happens is that the axis of symmetry is the y-axis. So when you reflect it over the y-axis, it's going to look exactly the same. And that's why the equation is exactly the same. So just wait for this calculator to wake up, and I'll show you what I mean. There we go. So negative x squared plus 4. The axis of symmetry is the y-axis. So when you reflect it over the y-axis, the graph will be identical. So the equations are the same. Describe a sequence of transformations to transform from the graph of y equals the root of x to that equation. This is a standard of excellence question, and part of it is because you have to remember to take the b value out as a common factor to get the correct h value. So when you divide both terms by negative a half, that minus 4 becomes a positive 8. And so the first thing we see is we have a b value of negative a half. So that will reflect the graph over the y-axis. And it will also shift the graph 8 units left. Pardon me? And then the plus 10 at the end means it'll shift 10 up. Oh, I forgot to talk about the horizontal stretch as well. After it reflects over the y-axis, it'll horizontally stretch by 2. Come on. Because because the horizontal stretch factor and the b values are always reciprocals of each other. All right, so for the next question, we'll use this graph. For each transformation indicated, where are the invariant points? So the first transformation is negative f at x. So when a is negative, that reflects the graph over the x-axis. And when it reflects over the x-axis, the x-intercepts are invariant. Our x-intercept is at 0.5. The second equation, f at negative x, when b is negative, it reflects over the y-axis. So the y-intercept will be invariant. That'll be 0.3. X equals f at y, that is one of the notations we saw for the inverse. And when the graph, you take the inverse of it, the invariant points will be on the point, on the line, I should say, y equals x. Because we learned that the inverse is a reflection of the original function about the line y equals x. So whenever a graph reflects about a line, the points that are on that line are invariant. That's what we did for the first two answers to this question. No different with the inverse. Reflections about the line y equals x, so that's where our invariant point is. And our invariant point, or our points on the line y equals x, are where the x and y values are the same, which is 0.1. 0.1 is at the point -4, -4. It's on the line y equals x. So that's where the invariant point would be. Number 12, verify that f at x is the inverse of g at x. So basically you are getting the equation of the inverse. So remember to do this. We start with the original equation, only we put y equals instead of f at x equals. Our first step for finding the inverse then is to change x and y around. And then you solve for y, get y by itself. So if you add 3 to both sides, so that x plus 3 equals 2y, and then y is found by dividing everything by 2. So instead of 1x, it'll be 1/2 x plus 3 over 2. And so you've just shown where the equation of the inverse came from. Yes? Will there be? There could be. Like, I have no idea. I won't see it till an hour after you guys start. So, well, the most predominant one is relations and functions because that's where transformations are, and we did transformations in almost every chapter. So, no question, transformations will be tested more than anything else. Yep. A restriction on the domain of f at x equals x squared plus 4 so that the inverse is also a function could be what? Well, if you look at the graph of x squared plus 4, that is the graph of x squared shifted up 4 units. That's what it looks like. The inverse, instead of starting at 0, 4, the inverse would start at 4, 0. Remember, all the points on the inverse are found by taking the points on the original graph and switching the x and y values around. And it'll open up to the right instead of up. Remember, the inverse is a reflection about the line y equals x. So that is not a function. It's not. So what restriction could we put on the domain of f so that the inverse is always a function? So if we only had, let's say, the left side of the original graph, the left side only, that would correspond to the bottom only of the inverse. And the bottom only, without the top, by itself, is a function. So you could say that if you restrict the domain on the original graph so that x is less than or equal to 0, and only did that part, then the inverse would only be the bottom part of the second graph, and that is a function. Or we could also say, take the right side of the original graph only. That would correspond to the top of the inverse only. And that by itself is also a function without the bottom part. So there's two possible answers for this. Either x is greater than or equal to 0, or x is less than or equal to 0. Less than or equal to 0 is not an option. So B is the correct answer. Yeah. It would only be on x. So we've got this graph of f. We want to sketch the graph of the square root of f and also state domain and range. So a couple things to notice here. And, well, one thing that's missing and should have been there, arrows on the graph. So put those on there. But we had a series of steps that we followed to graph the square root of a function. The first thing we talked about were invariant points. To get the points on the new graph, you're taking the square root of f at x. You're taking the square root of the y values. So when y is 0, which are the x-intercepts, the square root of 0 is still 0. So that was our first set of invariant points, where y is 0. We also have a set of invariant points where y is positive 1, because the square root of 1 is still 1. Secondly, when y is negative, which is below the x-axis, there are no corresponding points, because you cannot take the root of a negative number. We can find a couple more points here by taking this point there, where y is 4, the square root of that is 2, so the x value isn't going to change, but you take the square root of the y value. Same thing with this point over here, where y is 4, the square root of that is 2. So the x value doesn't change, it's just the y value. And then we also saw that between the two invariant points, the new graph is slightly above the old, and then it goes below the original graph. Between the invariant points, the new graph is slightly above the original graph, and then it goes below. There's the new graph. The domain of this we can do it in two parts. From negative infinity to negative 3, which is included, and then from positive 1 to positive infinity. So that's using interval notation. The range goes from 0 up to positive infinity. Or we could say y is greater than or equal to 0. It's and. Yeah. That's set notation. You could. Probably not. But I can't say for sure, but I doubt it. So this next question also deals with square root functions. And we just finished saying that your invariant points occur when y equals 0 and y equals 1. Because when you take the square root of 0, you still get 0. When you take the square root of 1, you still get 1. Our invariant points are where y equals 0 and y equals 1. So to find where the invariant points for this graph is let y or f at x equal 0, let y or f at x equal 1, and solve for x. So for this first equation, we'll add 3 to both sides, and then multiply by 2. X will equal 6. Remember, that was where y equaled 0, so that'll be the point 6 comma 0. For the second equation, add 3 to both sides, gives us 4 on the left. Multiply by 2, and x equals 8. And we found this when y equaled 1. So there are the two invariant points. 6 comma 0, 8 comma 1. I said many times, don't be surprised if you see a question on the exam where you have to find either the x-intercept or the y-intercept for some function. And they're all done the same way. The x-intercept, in this case, we're asked for, it's always where y equals 0. If you want the y-intercept, it's always where x equals 0. But in this case, we want the x-intercept, so we're letting y equal 0. So now we need to solve for x. I would subtract 3 from both sides. I would then divide both sides by -2. So it'll be -3 over -2, which is positive 3/2, equaling the root of x plus 4. I then would need to square both sides to get rid of the radical. So that'll give us 9 over 4 equals x plus 4. And then when you subtract 4 from both sides, it'll be 9 over 4, take away 4, which with a common denominator would be 16 over 4. Or you could write the 9 over 4 as a decimal, 2.25, it doesn't matter. Either way, this gives us -7 over 4. And it does say to the nearest hundredth, -1.75. Remember that there are no negative answers for numerical response, but for written response, there would be. There's no place on the numerical response portion to bubble in a negative sign. So if you're doing numerical response and you get a negative answer, you've made a mistake. And remember, there's so many of these questions you can check on your graphing calculator. Right? So you can check this on the graphing calculator. Once it wakes up, put the equation in here and then find the x-intercept or the 0. Doesn't look like it wants to wake up, but you can do that. There have been questions on diploma exam where they ask you to algebraically factor a polynomial, so you've got to show some algebra. We said that it is okay to use the graphing calculator to punch the equation in and find the first x-intercept. And so you could do that. I might have to close it completely and then restart it. You can put that equation into y equals, graph it, and find the first x-intercept, the first 0. Doesn't matter which one you use, but once you have your first x-intercept, you'll have your first factor. There we go. So it's x cubed minus x squared minus 8x plus 12. So it looks like negative 3 is an x-intercept. So if we go trace and let x equal negative 3, y does equal 0 there, so that confirms it. Negative 3 is an x-intercept. So x plus 3 would be a factor. And so we're going to divide the polynomial by x plus 3 to get the remaining factors. But remember, we change it to x minus 3 so we could add as we're going along. So I'm doing synthetic division now. And remember, you got to make sure that your terms are in the proper order, descending order of power, and that there's no powers missing. If there's an x squared missing, you include it with a coefficient of 0. Or if there's an x term missing, include it with a coefficient of 0. But there were no missing terms here, so we didn't have to worry about that. Copy down the first number, multiply, and add. Multiply, and add. Multiply, and add. And we have to get a remainder of 0. That's what that last number is. Because x plus 3 is a factor, it has to divide evenly, meaning you shouldn't have any remainder over when you divide. So not only have we confirmed that x plus 3 is a factor, but now these three numbers tell us the answer, the quotient. It would be a second degree polynomial because we divided an x cubed by an x. So it'll be 1x squared minus 4x plus 4, which can be factored. That's a quadratic. The factors there are x minus 2, or x minus 2 all squared. So there's the factors. So again, the fact that you're doing this synthetic division, there's your algebraic. That's the algebra. The difference between this next one is that it's a fourth degree, so we're going to have to use synthetic division twice. So 2x to the power 4 plus 3x cubed minus 17x squared minus 27x minus 9. Once again, it looks like negative 3 is an x-intercept. And it is, because at that point y equals 0. Negative 3 is an x-intercept. So x plus 3 is a factor. Again, we would have changed it to x minus 3 so that we can add as we're going along. So the terms are in the proper order. There's none missing, so you don't have to include any coefficients of 0. Whoops, I shouldn't have put the x there. Just the minus 3. So we multiply and add. Multiply and add. Multiply and add. Multiply and add, and we get the remainder of 0 that we needed to get. So this confirms not only that x plus 3 is a factor, but also gives us our quotient. And in this case, we divided a fourth degree by a first. That'll give you a cubic. This will be 2x cubed minus 3x squared minus 8x minus 3. which we now have to factor the third degree polynomial. We can go to our graphing calculator and pick out another x-intercept. We learned that you don't have to retype the new equation in because the zeros, the x-intercept of what's left, will be the same as the remaining x-intercepts on this graph. So it looks like maybe -1 is an x-intercept, and it is. So therefore x plus 1 would be a factor. We would change it to x minus 1 so we can add as we're going in. Remember, now we're factoring 2x cubed minus 3x squared minus 8x minus 3. 2 times -1 is -2, and we add. -5 times -1 is +5, and we add. -1 times -3 is +3. We add and get our remainder of 0. So when you write your factors, don't forget about the x plus 3 factor that we found from the first synthetic division. Then we have our x plus 1, and then we have 2x squared minus 5x minus 3. And that quadratic can be factored. Minus 3 there, plus 1 there. That'll give us minus 5x in the middle and minus 3 at the end. So now we've done our complete factors. Right, and you can check these against the graphing calculator. If 2x plus 1 is a factor, that means -1/2 would be an x-intercept. -0.5 is an x-intercept because y equals 0. Our last factor is x minus 3. That means +3 is an x-intercept. And it is. Y does equal 0 when x equals +3. Right, so we can always check these. Which of the following is a factor of that? Well, because it's a multiple choice question, you don't actually have to physically factor that. You can put the equation into your calculator and check that way. So I've got 4x to the 4th minus x cubed minus 8x squared minus 40. So no x term here. It's just minus 40. So if you graph it, if x plus 2 is a factor, that means -2 is an x-intercept, which it is. If x minus 4 is a factor, +4 would be an x-intercept. It's not. X minus 6 would mean that 6 is an x-intercept. It's not. And x plus 8 means that -8 is an x-intercept. It's not. The only one that is -2, which means x plus 2 is a factor. Number 19 says, if x plus 2 is a factor of f at x, determine k. So to do this, we use the remainder theorem. We said that if you have a polynomial, and in this case you're dividing by x plus 2, you can find the remainder by evaluating for p at -2. In general, we learned that if x minus a is a factor, p at a will equal 0. So the value of a is always the opposite of what it appears to be because you're always comparing it to x minus a. In order to get x plus 2, you'd have to punch in a negative 2 for a. And then the minus minus would become x plus 2. So when x is negative 2, this whole equation will equal 0. When x is negative 2. The remainder theorem says that when you divide a polynomial by x minus a, you can get the remainder by finding p at a. And if x minus a is a factor, that means the remainder is 0. So p at a would have to equal 0. Negative 2 cubed is negative 8. Negative 2 all squared is 4 times 3 is 12. Negative k times negative 2 is positive 2k. Negative 8 and 12 is 4, plus 4 is 8. Subtract the 8 from both sides and divide by 2. And there's our answer. K is negative 4. And again, you could check that on the graphing calculator. If k is negative 4, the equation would be x cubed plus 3x squared. If you let k equal negative 4, minus negative 4 becomes plus 4x, and then plus 4. If you graph this, to make sure that x plus 2 is a factor, that would mean that negative 2 is an x-intercept. If I go into trace, I let x equal negative 2, y does equal 0. That confirms that negative 2 is an x-intercept. So you can check it. Can't hear you. Remainder theorem says that if a polynomial p at x is divided by x minus a, you can find the remainder by evaluating p at a. That's what the remainder theorem says. If p at x is divided by x minus a, the remainder can be found by evaluating for p at a. That's what the remainder theorem says. And in this question, because x plus 2 is a factor, the remainder would be 0. That's why we let p at a equal 0. This next one, we're identifying which ones are real polynomial functions. And so what you have to remember, to be a real polynomial function, you cannot have a variable in the denominator. Cannot be any negative exponents. Rational exponents. Or variable exponents. So basically your exponents have to be natural numbers. So the first one is, second one is not, because the x to the negative 1. Three would be, doesn't matter that you have an irrational coefficient. 4 is not, because you have 1 over x. That's the same thing as x to the negative 1. And 5 is not, because you have 2 to the x. So the only ones that are real polynomial functions would be equations 1 and 3. Number 21, sketch the graph of a fifth-degree polynomial function with one real root of multiplicity 3 and a negative leading coefficient. So, if it's a fifth degree polynomial, we learned that there has to be 4 direction changes. If there's a negative leading coefficient, because the degree is odd, you compare it to a line. A line with a negative leading coefficient means it's a negative slope. The graph will rise left and fall right. So that's what the negative leading coefficient does. And if it has one real root with a multiplicity of 3, that means a point of inflection there. A point of inflection is where the concavity changes. So, I mean, there are infinitely many graphs that you could draw. Doesn't matter. But it has to rise left, fall right. There has to be one x-intercept with a multiplicity of 3, which means there's a point of inflection, and it can be anywhere. So let's just say we're going to put the x-intercept at -3. So it has to rise left and fall right. So there's just one example of what it could look like. There's our point of inflection at -4. That shows a multiplicity of 3. The point of inflection actually counts as 2 direction changes. So that's 2 direction changes. We got a minimum here, that's our third. A maximum there, that's our last, our 4th direction change. And the graph rises left and falls right. Remember, if the multiplicity is 2, that means the graph bounces off the x-axis there. And if the multiplicity of 1, it just simply crosses through the x-axis. We want to graph that one. It says accurately sketch the graph, label any key points. So, first thing is we have x minus 2 is a factor, so 2 is an x-intercept. 2x plus 5 is a factor, so -5 halves, or -2.5, is an x-intercept. X plus 4 is a factor, which means -4 is an x-intercept. But because it has a multiplicity of 2, the graph's going to bounce off the x-axis there. This would be a 4th degree polynomial. You've got an x, a 2x, and an x that's squared. That will give you a 4th degree polynomial. So we need to compare it to a quadratic. The leading coefficient here is positive 1/4. So it'll act just like a quadratic with a positive leading coefficient. It'll rise to the left and it'll rise to the right. We can find the y-intercept by letting x equal 0. So if I let x equal 0, 0 take away 2 is -2. 2 times 0 plus 5 is 5. 0 plus 4 is 4. Squared is 16. So I think that's going to give us -40. I think let's just do 1/4 of 16, which is 4, times 2 is -8. Yeah, -40. We don't really have room on this graph for our y-intercept, but it's going to be way, way down at the bottom. We know it's got to rise to the left. We know it has to bounce off that first x-intercept. It's going to have to go up and then turn down to go through the next x-intercept. It's going to come way down to -40 before it turns up. And then again, the graph rises to the right. So there's a sketch of the graph. For the domain, there are no restrictions. So the domain would be all real numbers, or from -infinity to +infinity. To find the range, we'd have to find the value of this minimum point. It's down here somewhere. And to do that, we will use our graphing calculator. So if we put this equation in here, 1/4 is 0.25 bracket x minus 2, 2x plus 5, and x plus 4 all squared. So I know that my window for y, my y minimum, is going to have to be something, we found our y-intercept to be negative 40, so let's let our y minimum be negative 50. Hopefully we can see the graph where the minimum is, which we can. Second function trace, we want the minimum, which is number 3. My left boundary is fine there. I'll put my right boundary at 2. So if I round to the nearest tenth, it's at approximately 46. Now on a diploma exam, they'd give you something to work with an exact value. But there's the range. The zeros, well, we kind of already done that, right? They are the x-intercepts. It says determine, so to show where they come from, we take each factor and make it equal to 0. Remember, the word determines, you got to show your work. So that shows where they came from. Okay, I'll do this next question and then that'll be it. So you've got the graph of that polynomial function. It asks us to determine the minimum possible degree and then the equation in factored form. So there are 1, 2, 3 direction changes here, which means it'll be a 4th degree polynomial. We know that the degree is even because the graph opens downwards. That also tells us that the leading coefficient is going to be negative. So again, this is a minimum degree of 4. Now the reason the word minimum is used is because this x-intercept of positive 5 will have a multiplicity of 2. The graph bounces off the x-axis. But we learned that actually it could be any even number. It could be 4, it could be 6, it could be 8 multiplicity. But we're using the minimum possible degree, which means that this is a multiplicity of 2. And now, to find our equation, you have to remember that you're always going to have a, which represents the leading coefficient. We know it's going to be negative because the graph opens downward, but we need to find out negative what. Because negative 3 is an x-intercept, x plus 3 is a factor. Because positive 1 is an x-intercept, x minus 1 is a factor. And because positive 5 is an x-intercept, x minus 5 is a factor, but that one has to be squared. Because again, the graph bounces off the x-axis. So that's a multiplicity of 2. To find out what a is, we have to use some other point on the graph. And we have our y-intercept right there. The y-intercept is at the point 0, 5. So we can sub that into the equation that we've written down and then solve for a. Y is 5 when x is 0. 0 minus 5 is negative 5. All squared is positive 25. So 5 will equal negative 75a. And then we'll find a by dividing both sides by negative 75, which is negative 1/15. And now we can say the equation is y equals negative 1/15 bracket x plus 3, x minus 1, x minus 5 all squared. There's the equation of that polynomial function. Okay? All right.